языке скажу. О, понятно, спасибо. Понятно. Так. We have rather sad news of personal characters, my friends. The mathematical community, and especially the, let me say, algebras in analysis community, sustained a great loss. Several days ago, an outstanding mathematician, Professor Harold Gard-Dales, passed away after very heavy and very unpleasant, if I can use it, illness, quick and devastated. And for some people, this loss is especially sorrowful because some of us were his personal friends. Especially it concerns me and Maria. We were very close friends with Garth and his charming wife, Joanna. So I suggest that this current meeting is dedicated to his fond memory, if you don't mind, my friends. No, and we let us be healthy and live.
Анар Яковлевич, а когда он приезжал в Москву в первый раз, Дейлс?
91 год.
91 год, да.
Да, это я помню, да.
Ну, вы-то помните, конечно, но это даже я помню.
Это вы, Селиванов, помнит. Это, yes. How it was just in another, let me say, life. No, well, it's a pity. It's a pity, indeed. Great pity. No, so now now we begin our current meeting. Our speaker of today is Professor Anar Dosi from Middle East University. How does it call?
Middle East Technical University.
Middle East Technical University. So please, we listen to you with great attention. Yes. So please begin. Yes.
Let me share the screen first. Is it all right with my screen?
Yes.
Okay, let me squeeze this one as well. Yeah. Okay. Yeah, certainly, first of all, my condolences to Professor Dales. I knew him personally as well. I met him in Denmark, and I bought his book as well, his famous book on Banach algebras.
Yes. And everybody has his wonderful book, Banach algebras and automatic continuity.
Yeah, that's right. Yes.
Encyclopedic and excellently written. No, and what about his results? Of course, special topic. But please excuse my interruption. Please continue.
Oh, it's okay. Yes, thanks. Well, I always talk about the deformation quantization stuff of the projective schemes. Well, briefly about, because it's a topic mainly some intersection of analysis and algebraic geometry. And I would say something on geometry, because the main our seminar members, they are oriented to analysis. I have to say something on the geometry as well. Well, so we know the main principle of the commutative algebraic geometry is a correspondence between the commutative rings and affine schemes. So what is a scheme? If you have a ring, you can get all the primes, prime ideals, and use the localization to generate the structure sheaf. And this sort of couple, that's called the affine scheme. Well, in general, X is a topological space, or X is a structure sheaf, right? If it locally looks like affine, it's called a scheme in general. Well, we used to say like commutative scheme, because all the stuff is commutative. Yeah, and this corresponded as a bijection between the commutative rings and affine schemes. So the first principle of non-commutative geometry to understand, so what kind of geometry stands behind the non-commutative rings or non-commutative algebras, right? Well, X would play the similar role, like prime ideals, maybe non-commutative stuff, right? Two-side ideals, and by somehow generating O of X, structure sheaf. So, but deformation quantizations are one of the methods of the non-commutative geometry. It's a way by somehow deforming the structure sheaf and making it non-commutative, the first task. And the second task to understand what we got as a result, how we can classify all these non-commutative schemes. So, roughly speaking, non-commutative schemes means, again, topological space and the structure sheaf, which is a sheaf of non-commutative rings or algebras. Well, roughly speaking, so again, it must be within sort of category of non-commutative algebras. So that's important. So let me mention like the first key result and the first powerful result due to Yekutieli, like an algebraic version of the conservative result, established a real link between formal Poisson structures on a small algebraic variety and deformation quantizations. So what is that? So imagine again, we have a geometric object, x or x. We are deforming OX into an OX of formal power series of some variable h. So for formal power series, we can introduce sort of a new sort of multiplication, star multiplication. It's a classical multiplication. And again, some powers. Here we have some differential by operators. As a result, we are getting sort of a non-commutative structure. Well, certainly in general, there is no such general method of deformation quantization. Even this sort of construction is not factorial. It depends on a certain special class of algebras, non-commutative. Yeah, another direction was done by Bezrukovnikov and Kaledin using algebraic version of Fedossov quantization. So look, this is a typical example of a quantized scheme. Look, that's the scheme. X is a topological space. This is a structure sheaf of non-commutative algebras or rings. Well, on this part, H or X responds to its sort of commutant. So if you kill it, you're getting exactly, that's called commutativization, right? I mean, they're removing this part, you're going to get all of X. So you're turning back, actually. So that's a way how to quantize or deform it. Well, a similar structure we can see in Kapranov's model that I'm going to continue. I'm going to talk about 1998. It's they're sort of nilpotent thickening of the commutative schemes. This one is based on the commutator filtrations of non-commutative rings. I will explain what is that, all the detail. So roughly, we have an associative ring, a non-commutative. We can equip with NC topology, the special topology given by means of filtration. Again, I will explain below what is that. So, so it's a ring is called NC complete if it's halved and complete with respect to NC topology. Again, we can talk about this commutative structure. We can kill this commutators, ideal, two-side ideal generated by all commutators. And as a result, I'm getting commutativization, so some commutative algebra. So I can build up standard scheme, commutative scheme, right, as a topological space X. But structure sheaf is a key moment here. How to construct the structure sheaf? You need again to use the sort of localization, special construction over prime ideals. As a result, we're getting this couple. This is a non-commutative affine scheme within this context of Kapranov's model. Again, if you killed all the commutators, you're getting the O of X, the commutative one, as it used to be, right? So, well, for example, what will be a affine space? A, N, K, Q. Well, why Q? You're going to remove Q or not? Anyway, first of all, finding Q. Q means just we have a nilpotent Lie algebra of index Q, generated by a finite number of independent variables, x1, xn. Right? So you can take it formal spectrum. You can look at all this And then first of all, NC completion, then you can look at all the open primes. As a result, you're getting your non-commutative affine space. Again, as a topological space is the same, like is a classical affine space, n-dimensional. But structure sheaf has a nice description. Look, it's a commutative structure sheaf of the commutative algebra of polynomials, K of X. Y is a family of commutators in X. For example, you can choose a whole basis. So, but they have just finite number of them because out of this Q. So we have finite number of new variables. So as a result, you're getting a formal power C. This is over O, over my structure sheaf. This is my structure sheaf of the non-commutative affine scheme. Well, certainly you can do the same if Q is infinity. So you're going to get just lots of radical variables here, right? So for Y. Look, so it's a affine space of Kapranov's model of the non-commutative algebraic geometry. So concerning
excuse me,
sure.
question. Now, what does it mean in the case Q is infinite?
Well, yes, that's right. So Q infinity means just a free algebra. So you have to say as a algebra generated by X. Well, you know, there's
I understand. Exactly free algebra without restriction.
yeah, that's right. So total free algebra. Okay. Yeah, concerning projective stuff is a bit complicated here. Anyway, first I considered this one all details. I will explain the details here. So that we are planning to by somehow classify to describe using the concept of deformation quantization. So overall, we know what is that. It's we have to choose the analog. Whenever we have a commutative grade algebra, proj means the set of all homogeneous prime ideals, which doesn't contain all the positive homogeneous elements, as it used to, right? The projective space, right? For example, get the polynomial algebra and get the projective space, right? So there is a general formalism. What we have to do here, based on the set of the result, between the current sheaves and finally generate grade algebras. So there is another direction, made in several papers by Vandenberg and Artsen. This again, another special direction when we are using the twisted homogeneous coordinate ring, using an automorphism and invertible sheaf. Again, there are plenty of directions here what we can do. So, for example, you can do the quantum plane can be obtained by means of projective line, as this formula. Okay. So I don't like to talk about too much about the history, but briefly let me switch what I want to do here. So I will introduce this one, P projective space in the Kapranov models. You know the meaning of Q now, right? So this is going to be a projective space that stands behind of the SQ, again, universal enveloping algebra, the same. And the main challenge, how to classify all this projective schemes, for example, curves, surfaces, and so on. Non-commutative, definitely. Okay, that was introduction. Now I briefly mentioned some facts. Probably you know or not. I don't know. So briefly about. Yes, please.
Да. Да, здравствуйте, Борис Сергеевич.
Yeah, should I stop or?
Ну тут как раз у нас семинар вот этот алгебры в анализе. Ну ничего, если вот. Да.
Yeah, okay, so let me start. So S is a positively graded commutative ring. Look, that's S plus the set of all positive homogeneous elements. Proj is a related scheme. That's called projective scheme with a structure sheaf. How to define the structure sheaf? I will explain. For example, well, in the terms of quasi-coherent sheaf, what is that? So fix a module, graded S module. Then module defines a new sheaf that's called quasi-coherent OX module. So whose talks are given by means of localizations. So look at this notation, this P, localization, that's P. So first you have a normal localization. They are just ratios. Numerator from M, denominator is an element of the ring, but out of P. Both must be homogeneous, but they could have the different degrees. So inside of this, this again has a special grading, it's a graded SP module. Inside you have to choose the degree 0 submodule. So, and P is actually a SP submodule of degree 0 ratios. Okay, so, well, the same, you can use this formula, for example. You can get this is a localization with the denominators a little less. S is a fixed element. Then you have this formula. So D plus is a principal open set, is a affine subset. So if you look at this module, this is a SC module. If you localize, but now it's a normal localization, you will get the same stock. So what's the meaning of that? If you restrict this quasi-coherent sheaf into affine, you're getting just standard quasi-coherent sheaf over affine. Generated by means of the module MS. By the way, on the affine case, it just so there is a one-to-one correspondence between modules and the quasi-coherent sheaves. This corresponds as one-to-one, but here not. But locally, this guy can be is actually just normal quasi-coherent sheaf, like that. So I need to also explain what is meant twisted, because we're going to twist lots. So again, the same graded ring generated by S1 as S0 algebra. So for every integer, we can twist. Twisting means just shifting to the left L units. For example, twisted module, D's term is just MD plus L. The same, you can twist the original ring, for example, S, right? Shift it to L units. So twisted is again the graded module. So you can talk about the same sheaf, OXL is also a quasi-coherent sheaf, right? OX or just which is locally free OX module. Well, the tensor construction is also standard. If you want a two grade S modules, so you can tensoring them. As a result, you're getting again graded S modules. And we have this nice formula just for this quasi-coherent sheaf. Two quasi-coherent OX modules. If you're tensoring them, look at this side, the tensor product of the sheaves, and in the right we have just special module and related quasi-coherent OX module. So that's all about shifting, twisting. You can twist any sheaf. For example, F is a sheaf OX module. You can twist it by tensoring like that. OXL over X F. Well, this one is quite okay. For example, we have this sort of nice formulas. For example, get of M of L. This is a twisted module. I get the quasi-coherent sheaf, which means this one. As a result, you are getting a sheaf and it's twisted. And the same here, so some OXD twisting like that. Result, you're getting D plus L. You can twist structure sheaf DL, as a result, D plus L. And if you twist one more time, you're getting D plus L. Now, this twisting, for example, you can get this degree D homogeneous element and some global section of the sheaf. By tensoring them, you can be inside of F D plus L. So there is an action, right? SD global section. As a result, you're getting sort of section of F D plus L. Well, it's better, right? Global section. Now, what's the idea? I told you in the affine case, modules and quasi-coordinate sheaf, they are one-to-one correspondence. But that's not the case for the projective case. To restore the module that we wish to make it like a M tilde, like every quasi-coordinate sheaf, that means we need to twist them, get the global sections, and add them up. This is going to be graded S module associated with that. So now let me formulate some Q result from classics. So get any scheme, F or X module, then F is called a quasi-coordinate X module if locally, I mean for every open affine, it looks like that, N tilde for some module. This is a proper definition of a quasi-coordinate module or quasi-coordinate sheaf. So now that's a key result. Every quasi-coordinate sheaf on this projective scheme, like PROJES, looks like that. But this correspondent is not one-to-one again. So there are you could easily construct another modules with the same app. Right? That's a way how to restore the sheaf itself through its global sections. Because in the projective case, global sections can be really poor. This can be just, for example, field itself or very, very poor. But twisting and getting the global sections adding up, you can restore the sheaf itself. This is a first key result that we need for our further consideration. So now I mentioned here some elementary operations from the sheaf and their algebraic version. For example, whatever sheaf you have, you can draw the sheaf on the X to Y. This is a routine. Next, the morphism between the graded rings. It can be converted to a scheme morphisms. Again, you have S, T, X, PROJES, PROJ, T. You can get this set, and you know how to go back from Y to X, getting just inverses of the primes. Look, this is a map of our stocks. So overall, we are getting some scheme morphism from the set U to X. So locally, this map compatible with the affine morphism. Look, you can get this affine stuff, the morphism, and then you can get the affine scheme morphism. So all of them, they're compatible altogether. They're glued by means of all this affine morphisms. Yeah, there are nice formulas. I can skip them. So you can get module U. This is a quasi-coordinate module. We'll stick to U. Look at this formula. So to draw the sheaf from X to Y, or from Y to X, that means actually, in algebraic sense, if N is a module over T, it can be regarded as a module over S. Well, we can also prove it's twisted version. It's not so hard. Twisting here is a result is twisted here. Yeah, I can skip them. So next construction that I need, the disjoint union of projective schemes. Well, first, you know very well what is a disjoint union. So for topological space is a disjoint union as a topology, was the finest topology such that all embeddings are continuous. So X, disjoint X consists of all these unions, U1, U2. Well, if you want a sheaf here, you can restrict to a sheaf to every copy, right? Because every copy is a sort of open and closed there. So this is my notation Fi. Well, from algebraic point of view, disjoint union means just the direct sum. So direct sum responding to disjoint union of affine schemes. Here, some explanation, but briefly you can understand what is that. For example, if you look at the primes here, I mean primes in the sum, but every prime looks like that. For example, P1 plus R2. it always contains one of the copies, R1 or R2. If you localize here at prime, it's the same as R1 at P1. So this one exactly means my scheme is just a disjoint union. So let me say what I want to say. Look, if you get spec R1, spec R2, they are disjoint union, right? That will be exactly spec R1 plus R2. So disjoint union is a scheme. Look, it looks like that exactly. Well, a similar structure takes place for the projective schemes. So you can get the projective scheme. Again, look at this sum. Sum again is graded. If you localize at 0, you can have the same sum. And Stokes, again, the same formula is true for stops. So it's every P. So that means, again, that means the disjoint union of projective responds to the project of this sum. So that's all important. Okay, now let's look at this case. Whenever x1, x2 is x. In this case, we have an initial map. So x disjoint union x is just identity at every copy. So we now have a continuous map. Well, having a sheaf here, you can look at every copy and draw it to here. It's going to be a sum, right? That's quite natural. F1 and F2. It's not so hard to prove it. Just whatever sheaf here. If you draw it here, you're going to have a sum. Well, from algebraic point of view, in the projective case, this map, the sigma map, responds to just diagonal map. This one is easy. So look, the graded ring, look at the diagonal map. Then you can calculate the proj. You can generate the same set U and look at the map in a backward. So if you look at this map backward, you will get the same morphism sigma. So this couple is a scheme morphism. And in this case, this sigma cross, the morphism of shift, responds again to the diagonal map. Anyway, so this the famous map sigma for us, it's important. It just represents diagonal morphism. Yeah, one more stuff left from the classics. What is meant closed immersion? What is meant closed subscheme? It's not so easy stuff. So in general, so we have a scheme. By closed subscheme, we mean a morphism of schemes. So I is a homeomorphism of Y onto closed subspace of X, but sheaf morphism should be onto. In this case, so we have a sheaf of ideals. That's called ideal sheaf of my closed subscheme. Okay, so yeah, let me skip this part and explain what we need here. So the key fact, every quasi-coherent sheaf of ideals is actually an ideal sheaf. So whenever you have a quasi-coherent sheaf of ideals of O of X, it looks like that always, with respect to uniquely defined closed subscheme 1. Yeah, the same. What is one projective scheme? It's a closed subscheme of P and K. Again, P and K is a portion of the commutative algebra of polynomials of n+1 variables. Yeah, you can twist it also. We know how to twist. We can generate this one. And let me just formulate from classics the second key result. Yeah, so every projective scheme looks like that. So it's given by means of ideal now of the original ring S. And it looks like that, proj of S of 1. Okay, so that's enough from the classics. Now let's switch to non-commutative stuff. Non-commutative variables. So we're going to fix n+1 variables. Okay, so we know this is proj pkn. Now we switch to SQ. universal enveloping algebra of the free nilpotent Lie algebra. So this nilpotent Lie algebra has a natural grading like that. So this is a subspace of all Lie monomials in X of the length R. So look, that's the meaning of this gradient just. So we can add up all the paths from starting from n, just gn. I mean I more than equal n. Anyway, it's just a gradient nilpotent Lie algebra with standard gradient. So now let's choose our variables y, yi. We can choose some base here, and this is a disjoint union. All together, that's called the radical variables. So x and y, this is my original variables. These are radical variables, commutators. All together, we have a notation z. So as you know, the Poincare-Bikov-Witt theorem, like all ordered monomials, turns out to be a basis for this SQ. Or that means SQ is actually a formula as a vector space looks like K of Z. Well, we can introduce some weights here, like degrees. We can assume the degree of x is 1, degree of ym is n plus 1, whatever degree of non-ordered monomials will be some. This one generates some sort of order here. We can detect every member of the base with sort of weights. So look, we have a notation like curved alpha means just degree of the ordered monomial Z alpha. Now RQY, let me pick up the subspace generated by all powers, ordered powers of the radical terms. It's a unital subalgebra of SQ generated by commutators. Well, it has also natural grading. Look, M here. M means I can look at all these combinations whose this weight is M. Again, we have grading, so it's a graded algebra. Sm is inside of S plus M. And for the SQ, we have this formula, right? This is quite easy. S stands regarded Q as a vector space. As a vector space. Now, I will formulate my partial main result because, well, by somehow, and thereafter I will try to explain some detail because I need to cope within that time period. So now we're going to fix any projective scheme. So you know, projective scheme means there is a closed immersion inside of P and K. It's a commutative everything here. So we have a structure sheaf here. This is O. This is twisted one. I can draw it back. That's called very ample sheaf. Now, look, this is a formal definition. At the first glance, it will be a bit complicated. No idea what's going on, but you can try to catch up what I want to do here. So by geometric quantization of the scheme, we mean a couple, Z and D. Z is a family of projective subschemes of Y. So inside of Y, we are picking up some family of subschemes. Well, 0, if J responds, is just all scheme Y. But for large, after some step, it's just empty. Yeah, empty is important for us. We're going to plug in some way empties. So Z is just family of subschemes. D is sort of distribution function. So for every index alpha, we have Z of alpha instead of ZD alpha. Well, if alpha has one more index, Z alpha prime will be a closed subscheme of Z alpha. So they're not just distributed, they have some order between them. Now, for every M, I'm picking up all the Z alphas whose weight is M. This is going to be a project closed subscheme of the disjoint union. Look, this types. And there must be some scheme morphism such that this diagram commutes. Well, the same sigma as I told you above, the same sigma which is identity map on every copy. So this scheme morphism should be compatible with this sigma. Then I can pick up all the structure sheaves here, look OZI first, twist them, and draw them all of them onto Y. Second moment, what we need, there must be some link between this sheaves. Well, they are sort of differential operators. I will explain a bit later what they are. So imagine we have partial derivatives, some adjoints, right multiplication operator, and something like that here. Anyway, they're not so important now. Just they have some link between OYM and some others, OYT plus L plus Y in a twisted version. So what? If you have a geometric quantization of the projective scheme, then I can pick up all the structure sheaves of every subscheme, twist them exactly minus m units if weight of alpha is m, add them up, then get all this throughout m from 2 to infinity. For m equals 1, I can use the original structure sheaf and add them up. Look, as a result, you're going to get the special sheaf of noncommutative algebras, or noncommutative rings in our case. So this couple Y or QY is going to be a noncommutative scheme over K, being an NC deformation of this Y or Y with a structure sheaf. Well, certainly here we have to know what is an NC deformation. What is that? So what kind of noncommutative algebras we come up with in this result, right? Anyway, that's a general idea, right? So what's happening here? Get some scheme by somehow generating closed subschemes, and they are linked to each other, and also there are sort of differential operators between them. And then if you fold them up, you're getting sort of a new structured noncommutative scheme. Yeah, this is a partial result about geometric quantization, but at least it gives you an idea what's happening here. Yeah, now I can explain some moments, details, what has been NC deformation, more strongly mathematically, and what kind of noncommutative algebras we are covering here. So let me start again from the beginning again. So we have a noncommutative ring. Now everything is noncommutative. So we have a filtration here. What I'm doing, a ring again can be considered as a Lie ring, right? And I can take a T plus 1 member, or sometimes T's member of the lower central series of the Lie ring, and get the two-side ideal. So we're going to multiply them, and for all indices whose sum is F. This one will be FMR. So it's a two-side ideal, right? So this one generates a sort of filtration. That's called NC filtration. The terminology is due to Kapranov, NC filtration. So the ring is called an NC complete ring if it's Hausdorff, and complete with respect to NC topology. Well, optionally, you can complete it with respect to this topology, right? So what is that? NC complete ring turns out to be inverse limit of NC nilpotent rings. So NC nilpotent ring means whenever this filtration is dying out, I mean, it's trivial, right? After some large S is just vanishing here. So every NC complete is just inverse limit of NC nilpotents. Well, optionally, you can skip this filtration. You can talk about another filtration. You can get, for example, a filter base of two-side ideals, such that every quotient is NC nilpotent, and just J1 is I1. Let me recall, I1 means just ideal generated by all commutatives. Right? This is also called NC filtration. Yeah, NC filtration. This is going to be equivalent to to Kapranov's filtration, FMR. Yeah, if you kill I1, you're going to get commutative. And we have a quotient map. This one is called, again, commutativization of R. So concerning this filtration, I can look at these gaps and pull them up like that. This is just R by module. R by module.
Okay.
So the key property here, this sort of rings, they admit localization or rare localization, non-commutative. They are in turn again NC complete rings. Next, we can easily describe the formal spectrum. We can easily describe all two-side prime ideals. Well, in non-commutative case, there are several definitions of primes, and anyway, in this case, all of them are equivalent, and so we have a nice description. So this formal spectrum is actually reduced to a fine scheme of the commutativization up to homeomorphism. So the structure sheaf we know is given by means of these localizations, right? So it's a sheaf of NC complete rings. So this couple is called an affine NC complete scheme. So formally just inverse limit of this NC nilpotent schemes. I told you about Rn, right? You can kill this GMs and the NC nilpotents. And again, we can do the same construction. So now topology is discrete here, so no need for open primes. You can get all the primes and it's all fine. So in general, NC scheme is a ringed space, which is locally looks like affine NC scheme. Nilpotent or complete, doesn't matter. Now, the key definition, what is with deformation? So let R be NC complete ring with a filtration. A is a commutativization of R. Suppose R has an A module structure, not A algebra, such that all the stuff, GM, from filtration, they are A submodules. So this is graded structure, which also turns out to be A module, right? So we say that the ring is called an NC-deformation of this commutative ring if R by module structure of this grade R is actually reduced to its A module structure as a pullback through the portion map. So roughly speaking, all the gaps must be sort of commutative, roughly speaking. Then it's called NC deformation of N. Well, if it's NC nilpotent, we say the NC nilpotent deformation. So look, all the gaps R by module structures actually turns out to be A module structure. Right? Anyway, so we can talk about some maps in a backward. So this quotient map turns out to be a retraction. Well, as an example, for example, you can take this one, A, K, N, K, and C. So I told about in the introduction, so there's a formal spectrum of the NC completion. You can get the free associative algebra generated by X, get it NC completion. So this NC completion actually turns out to be NC complete deformation of the polynomial algebra in our sense. Yeah, that actually, we have this formula, Kapranov formula. It's a formal power series over Kx. Well, if you don't like Kx, we can replace Kx by Q. I mean, universal enveloping algebra of the free Newton-Lee algebra. Again, the same formula works. Again, ONCQ turns out to be NC deformation of Kx, but all the difference here, we have finite number of radical variables here. Why? So you know the structure, right? So module structure, so on the universal enveloping algebra, what should be module structure? So they are sort of diagonal operators. So if you get S, standard polynomial, its action to non-commutative expression, you're going to act in a routine way on every A alpha. This is a classical multiplication. This is a realization inside of SQ. So that's a S-boy module structure. Well, filtration, look, the filtration is clear. What we have to do, we have to take S's more than equal M. Here, we don't need to calculate this Kapranov filtration, it being a bit complicated. This one is much easier, and this is going to be equivalent to this one. So look, this formula for completion. You can calculate all the gaps. Gaps, they look like that. So the SQ by module structure is actually turns out to be S module structure. The reason is that if you perform the SQ by module structure here, all commutatives, they are going the other side. They're just dying out eventually. So that's why it just structure the same as an S module structure. So OQX is another example of an NC complete deformation of the polynomial. Okay, now I will try to introduce what is meant non-commutative projective space within this concept and how to understand its structure sheet. Well, here we have nice grading of my SQ algebra. Degree D means what? So you should pick up D minus 1 degrees of standard polynomials and for the radical side of degree M. But pay attention, degree M is in the sense of weight. Yeah, look, so overall, we are getting this sum. So this one is indeed a grading, E degree D, E plus D. So SQ has a nice new grading. It's a graded algebra. Again, we are doing the same. The proj SQ means let's pick up the set of all NC open graded prime ideals, which do not contain the sum. As a topological space is a standard projective space. Sorry, it should be K here. Well, but structure sheet is a bit complicated. Again, we have to use the localizations within the Kapranov's model. But not just localization, we have to use the degree 0 localizations. Yes, this is a NC scheme. And look, there is a nice description for the structure sheet. You should get the structure sheet of the projective space is a commutative, twisted minus m units, and tensoring by this stuff, and get this direct product m from 0 to infinity. So roughly speaking, again, that this means the degree 0 must be here. By the way, this formula actually within our framework of geometric quantizations. Do you remember I picked up some in a disjoint union, some copies of the projective space. So you need just to pick up if you write down the dimension, so this affine dimensional space, write down just this number of copies of the standard projective space, and then you can use exactly minus m twisting, right? And you should draw toward, again, the same space through the map sigma and fold them up. That's exactly the geometric quantization. Well, certainly I said nothing about differential operators, yes. Anyway, this formula that for structure sheet, OQ. So my non-commutative projective space is ready. Well, concerning filtrations, yes, we can do filtrations because there must be filtrations here, right? Starting from m to infinity. If you look at the quotient turns out to be coherent sheet. So it's a canonical filtration. There is also one way to just for description, maybe just for fun, how to understand the structure sheaf, well, in terms of formal power series. For example, if this one is a formal power series in Q minus 1 variables. So you need just to plug in, instead of this variables, this twisted sheaves, instead of multiplication, use tensor product over, instead of sum over, and instead of limits, direct product, just formula. If you plug in here, you will get the same formula for all Qs. So all Qs are sort of as a result of the functional calculus of the sheaves. Well, the moment is that this formal power series is also, we can detect how it's changing whenever you're passing to projective subschemes. For example, for curved surfaces, is nicely changing this F. Okay, so in general, so now that we need to shiftify the previous definition, because the time is squeezing me, I will just show you what is mean NC deformation of the scheme. So a couple, so again, we have a scheme, commutative, a couple is called NC deformation. So we have the filtration inside of fx. All this portions there is in nilpotent schemes. Again, we can also talk about this graded stuff. It has fx bimodule structure. Fx bimodule structure must be reduced to OX bimodule, OX module 1 through the morphism. Well, roughly speaking, is shiftifying the previous definition of NC deformation. So that's called NC deformation of this scheme. Yeah, look at the first Q result is telling you NC deformation of affine scheme turns out to be affine. It's a nice result, but let me say not trivial result. So deforming affine in our sense of our definition, the result has to be again affine. Well, then you can develop this theory. So what is the morphism of NC deformations? It's a quite long stuff. What has been closed immersion? So it turns out whatever morphism you have, it generates a morphism of standard schemes. Right? Yeah, I can skip this part, closed immersion in a reasonable sense. Okay. Yeah, look, concerning differential operators briefly. So what we have in a polynomial algebra, the same Z, we have partial derivatives. We can generate this sort of differential operators by factorials, d bar. Then is coming up the noncommutative functional calculus. The notations are joined. And let me also mention the nice formula due to Karashev and Maslov. So APZ, if you wish to calculate the commutator in any free algebra, so you have to use the partial derivatives and adjoins. Or if you swap them, it's going to be d bar here and adjoins here. Well, we have standard multiplication operators in SQ. And we have also left and right representations, right? Look, this is my differential operators, at least on the polynomial level, you can see. They are differential. So this is my partial derivatives, adjoins from the right, it's a d bar. Well, here there are some differences. They're completed by somehow each other. Or in the compact form. You can fold them up, delta J, nabla J. Well, again, the calculation can be done for this differential operators for some particular cases. You can easily do it. They're not so hard. But in general, if Q is large, so they're really complicated. Yeah, since time is going up, let me, yeah, the same differential operator, let me at least formulate my main result. Yeah, sorry for this long slides. So differential chains.
Okay.
Yeah, so let me just formulate the Shoikhet rule. Look, this is the main result. So if you have a differential chain, so by somehow slicing there, then you can do idea the same. You can get this modules, special modules, quasi-coherent sheaves, twisting them and folding them up. That will be your non-commutative schemes. Yeah, look in the geometric case, again, we are getting the same geometric quantizations. And finally, let me just show you examples. So for example, the union of two lines in PK2, so you're getting, look, this sort of formula for the structure sheaf. You can do two quantization, three quantizations depending on Q. This is a way how formal policy is changing. Okay, for example, that's a case of the pre-quantization. There are lots of commutators here. A list of differential operators. And finally, this formula for the structure sheaf. Yeah, anyway, let me stop here. Sorry for this long talk. Yes, please, questions.
Yes. So, thank you very much. Let us applaud. As it is. So, what are about questions or remarks or critics?
Question.
Question, давайте. Давайте question.
There was a point when was said that free nilpotent algebra is positively graded.
Yes.
So maybe all this construction can be applied to every positively graded Lie algebra.
Well, again, yes, that's possible. But again, this one means you should pass to some closed subscheme, right? You should factorize it by a certain ideal. And this one will be, yes, it lies within this construction. Is it because whenever you're passing some another Lie algebra, this is going to be quotient of the free, right? Then you need to pass the universal enveloping to generate the same ideal. And this ideal probably will generate a new closed subscheme. Probably from here, you can draw the same formula for structure sheaf.
Thank you. And another question.
Sure.
Okay. What about other filtration, not only Kapranov's filtration?
Oh, but there's a whole theory. I mean, the bunch of works in different directions.
Okay, yeah, I understand.
Yes, but you know that there are plenty of guys. They were, for example, Vandenberg. They have lots of papers in quite different direction. But every direction generates a quite independent theory. So plenty of works, right, in this direction. Yeah, this is one model, by the way. This is applicable for all schemes. This advantage of this direction. Because in the other directions, they're applying to special schemes, for example, special curves or something. But here you're getting any projective scheme and quantizing it. So we know how to do it. Just list of differential operators. You're applying, generating ideals, and getting this closed subschemes, getting their sheaves and fold them up, and look, your formula is ready. This is quite practical, by the way. This.
Okay. Thank you.
Okay.
Other questions, please? Well, so let us again thank the speaker for a very clear and good talk. Thanks a lot. And we
by the way, Alexei will upload the file into a problem system. You can see the file there.
Very
it's quite long. It's about 99 slides. Anyway, if you have any questions.
Yes, yes, I was afraid, in fact, because almost 1 hour passed, and you were about 1/3 of this.
Yeah, that's right.
Yes,
Yes.
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 Well, but on the other hand, the speaker can take hour and a half.
Yeah, anyway, it's my bad, sorry.
Nevertheless, yes. So we are grateful also for this, as usual, in such situations. Okay, so next talk will be of Professor Akbarov, most probably about, duality, high forms of duality, but he will say, of course, yes. And in this, we can say goodbye each other, yes, for a time, yes. And we shall see the next week. So all the best to everybody, and don't be ill. Bye.
Thank you. Goodbye.
Thank you.
Yeah, have a nice weekend. See you.
No,
Goodbye.
very good. Bye. Bye.
Bye-bye.
Goodbye.